Welcome back, everyone. Today, we're unpacking something that happens on your computer literally every single day, yet it stays completely hidden from view. We're diving into exactly how Linux boots. Think of this 5 to 10 second window not just as a boring loading screen, but as a lightning-fast, incredibly complex relay race happening deep inside your machine.
So here's the core mystery we're solving today. What exactly happens between that exact moment you press the physical power button and the moment you finally get prompted for your password? Now, I know some software engineers just call this process mere plumbing, implying nobody really cares how it works as long as the water flows. But honestly, the sheer volume of intricate sequential tasks that get completed in mere seconds is just absolutely fascinating.
Okay, let's map out our literal racetrack for today's explainer. We've got 5 stages. 1. Post and firmware. 2. The grub bootloader. 3. Loading the Linux kernel. 4. Welcome to user space. And finally, 5. Systemd, the ultimate manager.
Let's kick things off with Section 1, Post and Firmware. The absolute split second you press power, the starting gun fires, and our first runner takes off. This is a process called POST, which stands for Power On Self-Test. It's essentially a rapid-fire diagnostic procedure run by the computer itself. The system is just quickly checking the CPU, the memory, the hard drives, basically making sure everything is physically functioning. Now, if you've been around computers for a while, you know that in the old days, a successful post ended with a friendly little beep. Nowadays, well, they've kind of silenced that. You're really only going to hear a beep during post if something is horribly wrong with your hardware, which of course stops our race before it even begins.
Now, depending on your system's age, the hardware is going to hand off the baton via one of 2 paths. If you're on a legacy BIOS, it relies on a master boot record and this somewhat clumsy method called logical block addressing, or LBA. But if you're on a modern machine, you're using UEFI. That relies on a much slicker, modern GID partition table. It specifically searches for an EFI system partition, usually right around 512 megabytes in size, to find the very next runner in our race.
Which brings us to Section 2, the grub bootloader.
So, the hardware checks are done, and the firmware hands the baton right over to Grub. That's the Grand Unified Bootloader. It's the default bootloader on the vast majority of Linux distributions. And what's absolutely incredible about Grub is its tiny but extremely mighty footprint. Listen to this. On legacy BIOS systems using a master boot record, the initial part of this loader squeezed onto the drive is a mere 441 bytes, literally. From that microscopic starting point, it kicks off the entire operating system sequence.
Think of Grub as your ultimate safety net in your staging area. If you happen to hold down the Shift key or just frantically tap Escape at the exact right microsecond during boot, you'll actually see Grub's menu. It lets you choose between operating systems if you happen to dual boot, and it thoughtfully keeps older, known stable kernels available just in case a bad update breaks your system. Plus, it offers a recovery safe mode and even a command line shell for deep troubleshooting. But the main event, the reason it's really there, it loads the Linux kernel into memory, fires the start command, and then immediately completely exits the track.
Moving right along to Section 3, loading the Linux kernel.
The baton is now firmly in the hands of the Linux kernel, which acts as the core bridge between your physical hardware and your software. And this actually brings us perfectly to Linus Torvalds' golden rule for kernel development: stay out of user space. See, the kernel is this entirely self-contained environment. During this phase of the boot, most distributions won't even show you what the kernel is doing on screen. It's just quietly and strictly inspecting the system, setting up hardware, and loading drivers, completely isolated from the software environment that you, the user, are eventually going to interact with.
Now, to do all of this efficiently, the kernel relies on something called the init RAM-FS, which Grub loaded into memory right alongside it. Think of this as a sort of archive that acts as a temporary root file system. Why do it this way? Well, because reading directly from blazing fast RAM is vastly superior to relying on clumsy, inefficient BIOS drivers just to read from a spinning hard drive. It basically guarantees the kernel gets a clean, robust, and lightning-fast environment to initialize all those crucial hardware drivers.
And that takes us to Section 4, Welcome to User Space.
Once the kernel finishes all of that intricate hardware setup, it mounts the actual physical hard drive, takes a step back, and starts a single program. This program is assigned Process ID 1, or PID 1. It's the very first software process, and it stays running quietly in the background until the exact moment you shut your computer down. This right here is the absolute beginning of user space, and it's managed entirely by what we call the init system. And understanding this brings us to a major, and honestly sometimes highly controversial evolution in Linux history.
For decades, Linux relied on an init system called sysv, which dated all the way back to 1983. It basically relied on scripts and executed them in a highly linear, very rigid manner. It loaded exactly one service at a time. If you've been around Linux for a while, you absolutely remember the sheer agony of watching an entire boot process completely freeze up just because one single script hung. It managed the system state using these numbered run levels. But then we get modern multi-core CPUs, and this new system called systemd emerged in 2010. Systemd completely revolutionized the game. It's entirely goal-oriented. It figures out dependencies and loads services in massive simultaneous blocks in parallel. It completely replaced those old run levels with flexible, goal-oriented targets, like for example targeting a full graphical login screen and then charting the absolute fastest parallel path to get there.
Which leads us perfectly into Section 5, Systemd, the ultimate manager.
Systemd doesn't just start the computer. It treats absolutely everything as a manageable unit with staggering scope. It handles service units for background programs, socket units that listen for network connections, target units for grouping tasks. It's got mount and auto-mount units, so when you plug in a USB stick, Systemd is the one handling it. Path units can literally monitor a folder, and if a specific file drops into that folder, boom, Systemd triggers an action. It handles scheduled tasks with timer units, effectively replacing older tools like cron. It even manages hardware resources for specific processes using scope and slice units. It is truly, truly a massive piece of software.
To finish out our relay race, here are Systemd's final rapid-fire steps. Working entirely in parallel, it starts essential background services like syslogd for system logging. It sets up your networking configuration. It fires up high-level services for things like printing and scheduling. And finally, right as it crosses the finish line, it launches either Getty for a text-based terminal login or a desktop manager like GDM or LightDM to give you that familiar, beautiful graphical login screen. The race is over, your computer's ready to go.
Now, as a user, if you actually want to pop the hood on this powerful manager, you're going to use two main commands. You'll use systemctl to view and manage all those active units we just talked about, and you'll use journalctl to view your system logs. Now, a quick aside here. Systemd actually saves its logs in a proprietary binary format, rather than traditional plain text files. And let me tell you, this still ruffles the feathers of quite a few Linux purists, who firmly believe everything in Linux should just be a simple, readable text file. But regardless of where you stand on that debate, journalctl is how you read them.
If this deep dive has sparked your curiosity and you want to master these concepts even further, you should know the foundational source material for much of this architectural breakdown is an excellent book called How Linux Works by Brian Ward. It's an absolutely invaluable guide, and I highly recommend it if you really want to peel back the layers of your operating system and go way beyond the standard graphical interface.
We're going to leave you today with this somewhat provocative thought. We started off talking about a simple 5-second relay race, right? But we ended up with Systemd, a manager so incredibly complex, handling timers, networking, auto mounts, and resource allocation that many critics argue it really isn't just an init system anymore. Has it actually become an entire operating system in disguise? Well, it's definitely something to think about the very next time you press that power button and wait for your login screen. Keep learning, keep exploring, and we'll see you in the next explainer.